All right, our next speaker is Sean Hostetter, another former student of mine.
Hello.
And he's going to talk to us about blockchain.
Yep, I will do my best.
All right, over.
All right. Going to be talking about blockchain technology. As a little background, I'm not an expert in cryptography. I'll do my best to explain the cryptography behind it. But mostly I'm just interested in smart contract development, mainly on Ethereum. I'm trying to switch to Solana. It's a very new and Wild West technology. So there's a lot of sort of pipelines and stacks and paradigms and protocols. So originally this presentation was mostly on smart contract development, but I realized that's a whole can of worms. So I'm gonna try and focus. I have a bunch of resources, a bunch of links, and hopefully these slides will be shared to you. So overview. Most of this presentation is sort of in the form of a bunch of questions, because that's sort of the path that you follow when you go down this rabbit hole. I mean, because like to start, I mean, most people don't even know what a blockchain is. I mean, you know that it facilitates cryptocurrency, but I mean, even I think a lot of the huge investors in cryptocurrency don't know how it works. And then, yeah, so in terms of what is a blockchain, you got to ask why. So, and that reason would be decentralization. So we're going to be talking a little bit about that. Blocks, exactly their structure, digital signatures. How do we create a secure system so people aren't just spending everyone else's money? How does Bitcoin work? Bitcoin is sort of the foundation for blockchain technology. It pretty much defines the architecture of all blockchains, even if others do vary a little bit from it. And Bitcoin, the main protocols are like a proof of work, and you know, probably a big mystery behind it is how mining works, and you know, how that will keep running in the future. Then we're going to talk about the sort of different protocols between blockchain and a lot of new, or Bitcoin and a lot of new cryptocurrencies and new blockchains. That would be proof of work versus proof of stake. We'll get into that later. And then my sort of area of knowledge, which is the Ethereum blockchain, talk a little bit about NFTs and give you a bunch of resources on smart contract development. Things I won't go that deep into are, you know, the specifics about cryptography. You know, you can use a SHA-256 cryptographic hash function and not really know exactly how it works. Basically, you just have to know that SHA-256 will take an input and it'll create a 256-bit hash of it, and it doesn't matter how long your input is, but it'll create a unique hash, and you know, 256 bits. It's enough complexity that you're never going to just guess it. And then how exactly private keys are transmitted. I do go a little bit into that, but it's the sort of network side, like the P2P network, how that's facilitated. I have a little link right here. And it's pretty complicated. I'm not an expert on sort of network architectures, especially peer-to-peer ones. They get pretty complicated. How to set up mining nodes, I've never done it. I'm sure it's, I don't know, it's one of those things where you're getting into blockchain technology, two things people want to know are what the next big cryptocurrency is and how do I mine it. So that's not really what I'm interested in. There's a lot more utility to them than that, in my opinion. So first, what is a blockchain? So a blockchain is basically, well, the first says it's a ledger of information, typically transactions broken into blocks and managed in a peer-to-peer network. That's true in pretty much every sense, except the more literal definition would be that it's a chain of blocks. Basically, you break up information into blocks and then you chain them together somehow. So a linked list could somewhat be considered a blockchain if you guys are programmers, to an extent. But pretty much you can see that this diagram shows the chain of blocks, and each one block is connected to the previous block through a hash. And this looks sort of like a linked list. A lot of these blockchains use this sort of structure. It's not exactly exactly what it looks like. There's a lot of different visualizations you'll find. And just to ease some confusion, this is more of a diagram visualization of sort of the structure of the actual blockchain itself. A lot of the time when you look up blockchain visualizations, you get crazy trees and nodes and stuff. And usually those are visualizations of transactions. It can be a little bit confusing, but the basic structure is that each block contains certain metadata information. They're indexed, they have a timestamp, and all, some of the, like the index, the timestamp, those are for security reasons. You have data. This can be a whole bunch of things. On Bitcoin, your data, well, actually the whole block is sort of limited to this 1 megabyte size. So your data is going to be mostly transactional history in Bitcoin. But like we'll see with Ethereum, there's technically an unlimited block size, which allows you to create, giant monolithic programs. So each of these hashes, the interesting architecture of how a blockchain works is called a Merkle tree. It's talked a little about in the Bitcoin white paper. If you guys don't know what a white paper is, basically it's sort of like not an academic paper, it's more informal than that, but it's just very descriptive, sort of less intimidating than a research paper. It just very succinctly talks about everything. And actually, you go into the Bitcoin white paper and you see, 40 pages or so of information and diagrams and talking about cryptographic hashes and these architectures. But really, it's pretty easy to understand if you just read it. The Ethereum white paper is a little more daunting. It's very long, goes into a little unnecessary detail, but it's still, I recommend, they are the best resources if you want to learn about an individual blockchain, exactly how it works, is these white papers. And I'll be linking to those in the end. Yeah, I think I go a little bit more in these slides and how they hash together, so I'll save that. So how does Bitcoin work? That was the general explanation of what a blockchain is, but specifically Bitcoin has a few more specific protocols to it. Bitcoin, like the definition of a blockchain, is a long chain of cryptographically encrypted, that's kind of a redundant, hashes that stores balances in transactions. And then this third bullet point is basically talking about, like, it gets a little confusing. Like if you have this long blockchain each block stores transactional history. Basically, the problem you're trying to solve is that you're trying to decentralize the system. So if you have, say, a public ledger that anyone can write to, and say, like, everyone starts with an amount of money and then they write down their transactional history with each other. You get the problem of, well, if anyone can write to it, then they can just lie. And that's sort of the problem. So usually the way this is solved is centralization through, like, banks. They arbitrate for that. The purpose of Bitcoin is to decentralize, so we can't have that. So how do we decentralize this arbitration? And the answer is this peer-to-peer network of nodes that are constantly trying to verify transactional the relationships between transactions and make them consistent, and then push them to a fixed but growable chain of these blocks of transactions. And so it gets a little bit confusing. So if I have a local wallet, you're gonna be like, well, in order for sort of this to be, I mean, this is just a number that says I have a number, basically. It's a long address, and then it says I have another long address, and this represents a number of something I have. And that's pretty much what it is. You don't actually need to download the whole blockchain just to have a wallet with a value. Your wallet just needs to be valid on the blockchain. So that's how you can have something people call like a cold wallet. It's just it's an offline wallet. And as long as you're not making any transactions, the blockchain won't care about it. Now, the last bullet point is sort of about the mining system and exactly how blocks are added to the chain. That's sort of a problem. Like, how do we group verify that each block is true, and how do we sort of democratize the system? So this is another little diagram of how a blockchain looks. It goes a little more specific. You have metadata that's used to control, things like timestamps, solve the issue of sort of double spending. It's something I'm going to go into a little bit. Another various sort of security problems and attacks that are attempted to be solved using this architecture. The block header, basically, I'll go, actually, I don't think I have any diagrams on it, so I'll just explain it now. This is a sort of simplified view of the blockchain. Pretty much all you're seeing here is block headers, but there's way more information. You see there's transaction history. The actual transaction history isn't necessary to say you don't need transactions from 50 nodes ago to know the state of your current node. And that's the sort of beauty of the Merkle tree. Actually, I wonder if I do have a diagram of that. Not really. So a Merkle tree is essentially, you have, say, a block of data, and then you have child blocks of data, like any sort of tree. And you want to minimize the amount of data in each individual block to get a similar hash into the next block. And a hash is just essentially, actually, I'm going to go to a website to show you what a hash looks like. I think Jonathan actually mentioned SHA at one point. Bitcoin and most blockchains use SHA-256. I think there should be it's like just a little online generator. Yeah, so say I put just anything in, and you could see, regardless of how long the input I put, it's going to generate 256 characters. Well, 32 characters, 256 bits, which means that you can encode any amount of information. And while this is predictable in that the same input will always give you the same output, it's pretty much impossible to derive the input from the output. So, which means, say your a huge part of the validation is private and public keys. So how are you going to send a transaction, and how do we know it's you? And the idea of digital signatures is that you send your private key hashed with the message. Basically, you just concatenate your private key in the message to create a signature. So they don't have your private key, but they have your public key, which can be used to decrypt and make sure and validate whether it's your private key without giving it to you. That's one of the use of hashes is public and private keys. Another use is essentially creating this verifiable blockchain. Essentially, if any node changes, each node is determined by the state of every previous node, of every previous block. So if anything previous to it changes, then the hash will change, we'll know it's not right. If any transaction within a block changes, the header is a hash of every single child element. So you can trim off all the child elements once you have the hash, because if any of those things change, the hash will change and you'll know it's invalid. So in this way, you can create sort of a cascading level of complexity. You can have the full-on blockchain in every transaction, every piece of information that's ever been put into it. And that'll give you a lot of information. But if all you want to do is verify the validity of each block, or the validity of, say, the state of the blockchain as a whole, then technically all you would need is one hash. You hash all of the transactions and metadata, and then you include those in the header, and then you hash every single header up to the current blockchain, up to the current block. and then you have a hash representing the state of the blockchain. That last part isn't really necessary. You pretty much just want to hash all the transactions into the header so you can trim. It's called trimming the leaves, I think. This is the architecture of how public-private key security works. It's pretty simple, but it's important to understand that you're not really sending your private key. You are combining your private key with a message, and then on the other side, your public key knows the message and can therefore derive your private key. That's just the way they're paired. Not exactly sure the exact cryptography behind it though. So there's a lot of problems associated with this sort of system, with basically no human intervention in the arbitration. One of them is double spending. Basically, this is a system with delay. So what if I spend money in two locations? What if I want to give Bob money for an ice cream cone and then Larry money for a popsicle? How do they know? How can I send the same money two places? How does the blockchain know? How do they know? And the answer is that every node is timestamped. They have a timestamp that's hashed in, and it determines its place in the blockchain. So say, in every transaction, you sort of ping the entire network. So you make a transaction, you ping the whole network, you make another transaction, you ping the whole network. Maybe some blocks, some nodes will get that transaction, one transaction later than the other. Maybe there's sort of conflict. But for the most part, the first one you pinged out will be the one everyone sees. And so maybe one block, one node, basically a node would be any system in the peer-to-peer network that's mining, that's fighting to adjust blockchain. Maybe they are the first to get their block pushed, and your transaction, and one of your transactions get through. That would mean that if someone else was going through the calculations, another node was going through the calculations to try and push your second transaction, which involves the same funds, onto the blockchain, it just wouldn't work. The first block's already pushed and it's timestamped. So you'd get a failed transaction there. There's another sort of edge case that I'll talk about that involves more malicious intent than just accidentally, sequentially sending the same transaction twice. And I'll go through that, I think, the next slide. And that'd be called a race attack. Basically, the idea is that you're trying to get two of the same transactions pushed at the same exact time as to confuse the system. So before, if it's sequential, if you make one transaction and then the same transaction, most nodes will see your first transaction and that'll go through. And we'll go about exactly how these blocks are pushed by these nodes. But for now, just understand that you're pushing these transactions to these nodes, and they're trying to validate your transaction, put it into a block, and then put it on the next chain. And then every next block is hashed with, it contains the hash of the previous block, and that's how they're all sort of linked. So a race attack is an attempt to exploit double spending by creating a race condition. And so I say it can be prevented by an escrow contract. That's true, but it can also be prevented just by waiting, really to accept the deal. So you want to make sure that the payment you're getting really goes through, or that the same transaction isn't already pushed to the blockchain. Because the system is basically that if a transaction is accepted, it'll be pushed onto the blockchain. So if you wait to see if someone else accepts your same transaction, well, you probably don't want to accept that. And the way you actually wait to see other transactions, or you wait to get someone else's signature, is sort of the entire concept behind smart contracts. Bitcoin actually does facilitate these. They're not really called smart contracts because they're not that smart. they can only be very small, and they're just a very simple stateless scripting language that are pushed sort of like a transaction, and they're executed by nodes on the blockchain. There are variants of the race attack that involve a collaboration with a miner. Basically, if a miner can manipulate the transaction data coming in, they can actually attempt to push that node. But as we will see, it's very, very difficult for a miner to push fraudulent nodes. And really, that can also just be resolved with the same thing, just waiting to see the state of the blockchain. And then, so as for security, say people might worry like, oh, so people can theoretically submit fraudulent nodes or fraudulent blocks. So we call these dishonest nodes. Then couldn't they take a bunch of money away from someone else, and couldn't they, give themselves infinite money basically? This isn't really possible because of sort of the second security feature, rather the first that we talked about, which is the public-private key system. Funds can only be transferred out of a wallet, or rather data or information, because these don't have to be transactions. They're generally considered transactions, but we'll sort of go in that with the Ethereum blockchain. But you need public-private key validation. You need the digital signature per transaction in order to actually validate it. So even if they were able to push fraudulent transactions, it wouldn't matter because they're not valid and they couldn't be pushed to the blockchain. Now, so the only thing they would actually be able to do is edit their own transaction history because they have their own private key. So this is also known as a 51% attack. So I'm actually going to go to the next slide and then come back to this because the next slide is on mining. You sort of have to understand mining to understand how exactly a fraudulent node block might be pushed. So basically, there's a lot of confusion around exactly what mining is. Actually, really before, just a short while ago, I sort of had this idea in my mind of what mining was, and it turned out to be completely wrong. And so I'm sure there's a lot of people like that, where you sort of hear glimpses of what exactly mining is, and then you get that idea in your head, and then you just confidently spout it off, which is what I did. But it turns out it's way simpler than I thought. My original idea was that mining worked where basically the blockchain worked like it's some sort of monolithic pile of data, and you're trying to solve sections of it, and then you get to keep the pieces that you solve. That's not really how it works. All it is a ledger of transactions. So the way mining works is, the mining isn't only for the miner's gain. It's to push these blocks of transactions to actually support the entire system. And the transactional calculations are actually very lightweight. There's not much to be done there. And so really, when people buy these giant rigs or these giant warehouses of servers, of GPUs to mine Bitcoin or any other cryptocurrency, it's not all solving transactional data. Basically, there's this idea of proof of work in Bitcoin. And the idea is that your ability to push a node, or a block from your node, which will give you a reward, is based on your proportion of the total computation in the peer-to-peer network. So say there's only 3 computers of the same power. Each one is going to, I think I have the diagram of the next one. Yeah. This is from a video. It's a really good video. If you want a very simple explanation of all this stuff, it's linked here. Hopefully we'll get these slides out to you guys. Basically, each node is getting all these transactions. They're all getting the same transactions. They're all being pinged by these people making transactions. Then each one wants to push their own block, because if they push their own block, there's a set reward they get. So how you decide actually which node gets to push their block is through this proof of work function. Basically, it's a separate piece of data, a separate field on the block, and it's a validator for the entire blockchain. Basically, for each block, there is a set number of sort of keys, you could call it. This uses this similar SHA-256 encryption. And so, but there's no way to actually predict what the key is going to be. So, and you can set the complexity with how many zeros. That's something to do with the mathematics behind the cryptography. But this number of zeros affects how difficult it will be to find this special hash, this special magic number that will allow you to push your block. So all it's doing is flipping bits. When you're mining, you're just flipping bits and testing them. So it's completely arbitrary calculation. All this mining isn't actually doing anything to the blockchain. Really, all of the extra data is thrown out. And we'll get into sort of, I'm going to briefly talk about a different sort of idea behind proof of work called proof of useful work. It's pretty cool. But this is all arbitrary calculation. Now, the actual complexity to solve each block is time-based. So the blockchain, or the Bitcoin sort of protocol is that it wants you to solve a block every 10 minutes, and each block contains a maximum of about 25 transactions. So this is order to keep the value down, and also since mining introduces new Bitcoin into the system, you want to keep supply low. And at 21 million Bitcoin, the miners no longer get any reward. And every 210,000 new Bitcoin, or every 210,000 transactions or blocks, it's halved. It's sort of just it's a weird self-regulating system. And one of the questions you may ask is, well, if there's no reward, why would people keep mining? And the answer is transaction fees. You can include extra payments to the miner in your transaction. And so they can pick up your transaction if you pay. And that's the idea behind, once we run out of Bitcoin, what are the miners going to do? That's a question I have. So basically, this system makes sure that if you have a node of thousands, even just thousands of computers constantly, or if you have a family of nodes constantly trying to compute this hash function, they'll never be able to monopolize it. It takes a tremendous amount of work just to get one block out. So if you want to push a fraudulent node, you have to first solve this hash function and hope you get it first. So in the situation maybe that you do solve this, this hash function, you get your block of fraudulent data pushed. Now, every single time the blockchain is updated, every miner wants to take in the new chain. They want to get the most recent block so they can start on the next one. But if that, if the transactional data in that new block doesn't match what they have, they're just going to ignore it. And the reason they ignore it is because if there's a fraudulent transaction, then it's going to be a minority of the entire blockchain. If there is a real transaction, it'll match up with what everyone has, and they'll just move on to the next block. So in order for this fraudulent node to actually be pushed, it needs to consistently outpace every single other computer on the network. And that's why it's called a 51% attack. Basically, the only way that you can actually push a fraudulent node onto the blockchain, I keep calling them nodes, a fraudulent block onto the blockchain from a dishonest node, is if you have 51% of the total computing power, which is incredibly impractical. And even once you get, even if you have 51%, there's sort of a complexity. It's described in the Bitcoin white paper, where even if you have the majority of the computing power, you're trying to stick this transaction in the blockchain forever, meaning you have to consistently outpace everyone. So if just by chance, another node with their honest data pushes their block before you get your next block, then your entire tree is wiped out. Or rather, you can then continue to solve, you put in their block into your chain and then try to continue to solve it because this block needs to be there forever. So it's incredibly difficult to add fraudulent blocks. I don't think it's ever happened, actually. Or if it does, it's very minor. So it's an incredibly secure system, but due to the arbitrary nature of it, it's sort of incredibly wasteful. So that's behind mining. There's this little diagram here that I think it's from the same video. I think it explains it pretty well. You can see you have all these nodes, these miners, and then someone making a transaction, sends the transaction to each block. Each block is constantly changing their hash. They want to find the next value that will allow them to push their block to the chain. And here you have someone trying to push a fraudulent transaction that doesn't match up with anyone else. So all of these other miners are ignoring it because it just doesn't match them. So in order to actually, so now they're on a separate chain. They're both linked. The chain people are going to use is the longer one. So maybe for a little bit, people might use this, and you can actually push new transactions to the chain. The solution would be just to wait, really, because this chain will pretty much never last. This chain of all the other computers in the world is the one that's going to last, and then all your transactions will update. And then the transactions you made since then have also been broadcast to this longer chain, meaning that say you spend money on this chain, what's it going to do on this chain? Well, it'll still be spent. If you spent money you didn't have, say you had it on this chain, but you didn't have it on this chain, then it might succeed on this chain, but it'll fail on this chain. So the state of all of the wallets, essentially the balance of each wallet will then be updated. Went over that a bit. Useful things to note about Bitcoin, I sort of mentioned this. Block size limit is 1 megabyte. It's sort of an efficiency thing, which is funny. Bitcoin is not very efficient. There are only 21 million possible Bitcoin in every 210,000 blocks the mining reward is halved. It started at 50. The first one to sort of mine a block of Bitcoin was this man named, I forget the first name, it's probably a moniker anyway, Satoshi. And it seems like a lot of Bitcoin for not a lot of computation, because the amount of computation required is proportional to the amount of miners, the amount of nodes on the network. The difficulty of the proof of work hash is dynamically set to take 10 minutes. I think I mentioned that. Basically, the amount of zeros it sets on the target hash you're trying to find is what sets the difficulty, and that's dynamic. So each block takes 10 minutes. And now we're going to talk about other blockchains a little bit. And the two big ones right now are proof of stake and proof of work. So we talked about proof of work. Proof of stake is a system in which block push priority is assigned by the node with the greatest currency holdings. Basically, the whatever node has staked the most money. And this sounds like kind of a problem. It's what Ethereum uses, and Cardano and Solana, all the new big blockchains. It's far, far more efficient. Something like, I want to say like 400,000 times more efficient or something than the normal Bitcoin protocol, which allows you to do way more stuff with it. But there's the potential problem of centralization. They try to solve this by burning fees in certain places, like some of your gas. Gas is a transactional fee that's used in Ethereum, is burned, basically sent to just like a nothing wallet that no one has, no one uses. And so I'll talk about that a little bit more with Ethereum. Proof of useful work, I sort of mentioned that. So I think that hyperlink leads to a paper, actually. I'll visit that right now. And what's interesting is that, so you want to create a function that has a predictable complexity, because you want a block to be solved every 10 minutes. And you want it to be the same difficulty for everyone scaling with their computer power. Now, there's other sort of similar mathematical things that are sort of useful things that you can do with a function like that. And that an example is machine learning. Basically, machine learning, by the time you solve sort of your giant set of linear equations to get the weights you want in this machine learning model, it's sort of a set complexity. It's determined by how you set the entire thing up, how many layers you have, how many variables you have. So you could actually make the work they're doing just running through a machine learning system. I think there's certain problems associated with that, one of them being data. Usually machine learning requires a bunch of data. So if you wanted a different job for every block pushed, then they'd be required to probably download, anywhere from maybe a few hundred megabytes to hundreds of gigabytes, depending on what the job you want to push. So it would be sort of not very scalable with data size. But that's just one of the sort of ideas behind proof of useful work, is making this not a completely arbitrary function. So that's linked in there if you guys want to read that. Another system is proof of history. I linked this here. This is just a great explanation of proof of history. I don't quite understand it right now. Basically, there's this new blockchain, you might have heard of it, called Solana. It's sort of blowing up. It's very fast, and that's the main reason, is that it can be used in the financial sector. Problem with especially Bitcoin is it's very slow, because there's a max transaction limit on each block of about 2,500, and a block can only be pushed every 10 minutes. So it's slow by design, essentially, and that's another system to sort of keep people safe, but it's also not very good in the financial sector where time is a huge advantage. Now, so the way it works is, I think of some sort of queuing system where transactions don't just wait to be pushed to the next block as soon as the current block finishes. It creates a sort of queuing system where I guess transactions can be swapped out somehow. This seemed like a pretty good explanation. I understood it when I read it. I couldn't repeat it to you right now, but it's an interesting system. Solana uses this proof of history. It's called proof of history, but it's just sort of a more advanced proof of stake that allows for faster transactions. Interesting stuff. That's pretty much these protocols are the separator between these sort of blockchains. So when you hear about Ethereum versus Bitcoin, you're wondering, well, what's the difference? Is it just popularity? It's actually these sort of protocols that facilitate how much each transaction costs, how quickly the transaction is, how big can a transaction be, what's the complexity of sort of special instructions I can send, smart contracts. So that's sort of what these new architectures allow. So proof of stake, it's an alternative to proof of work. Instead of having a miner solve an arbitrary function, priority is assigned to the greatest currency holdings. There's a couple other problems, and with that, one of them is your ability to stake your currency holdings. Essentially, staking your currency holdings, it's sort of like setting up a mining node. I don't exactly know how to do it. I'm not really worried about that. It's something you do. You need a minimum of 32 Ether, which is something like $95,000. So not something I need to be too concerned about. But it essentially gives you rewards. You're locking up your Ether, I think, to somehow secure the system. I think usually if you're a node, you want to stake your currency to get privileges when you're mining. But it can also, if you're, say, just a buyer, you can stake your holdings to get priority queuing, which can be a problem. That's another problem that leads to centralization. Actually, there was an NFT, and I'll explain what an NFT is later if you don't know what that is. But think of it like a drop of very expensive collectibles on the blockchain, on the Ethereum blockchain. Uses a smart contract, meaning essentially a script to control transactions. And this script should limit the number each person can buy. And the general architecture of Ethereum should make it so everyone has a fair shot if they all use the same gas, and gas being the transactional fee. You can sort of choose your gas to see how fast you go. The problem is that these things get very expensive, so everyone wants a piece of it. It's sold out in something like 5 or 10 minutes, 10,000 of these things, or 7,000 for this one. Each one is, $200. People are paying $2,000 in gas on one of these. Someone exploited the smart contract by staking 500 Ethereum, which is millions of dollars, to get priority queuing, and got 1,000 of them when there was supposed to be a limit of 7. So they sort of monopolized the entire collection. This was a huge problem. Basically, it's a direct demonstration of how the system can sort of lead to monopolies. I mean, think of a contract, say Ethereum wants to go into the financial sector, and say you have a contract that controls the stake in your company. Essentially, you're buying and trading stocks of this company, and it's mitigated through this smart contract. The priority will be a huge problem. Time is a huge thing. If you are able to get in there early, say if this contract has built-in operating hours like the stock market, then the price will spike briefly after. And if you're the first one in, you're going to have the greatest advantage. So the person with the most money really can take advantage of everything. Actually, I think I can. This would be a good time to just give you a glimpse of a smart contract. So I think it's called Sevens. There's this website called Etherscan. You can look at all sorts of addresses. I'm sure it'll show up on Google search. Maybe it doesn't want to. Maybe they hit it. There's a way to find it. It's probably on their website. I don't feel like going through their website right now. But within minutes, you can audit the smart contract. Essentially, there should be a wallet limit. Basically, if you want to purchase one of these collectibles, then we need to make sure that you don't already have 1,000 of them. It's a very simple function. It's one line of code. And all of these contracts are fully auditable through Etherscan. When you publish it to the blockchain, you can look at all of the callable functions. You can look at the contract itself, the raw code it's written in. You can see what it's compiled to. You can see the holdings of the contract. You can see all the money passing through the transactions. So it's a very open system. But it also allows you to instantly see the flaws in some of these contracts. So now we're going to be going a little more into smart contracts. This slide is sort of based on the idea of the blockchain as a state machine, and that sort of influences the idea, I think, of Ethereum. They have stateful programs. Essentially, the smart contract itself can have a state. So, hey Josh, if it's say you set it into a certain state to deal with a certain type of transactions. Say you have a pre-sale for your little collectibles. You want only people who are whitelisted, essentially addresses that are set into an array in the contract, to be able to purchase. So you're going to call a function probably called pre-sale or pre-mint. And so you want to be set in that state so no one else can mint. But also after the fact, after pre-sale is over, you don't want to enter in manually every single address to a whitelist so they can use the pre-mint function. You want to change the state of the contract so it accepts all transactions. And so in that way, these Ethereum smart contracts have a state. Now going back to this is sort of about how the blockchain can be seen sort of as a state machine. Every transaction is like a transformation function that changes the state. And the idea is that you can use contracts or scripts in Bitcoin to actually, determine multiple inputs to determine the state. And so in this case, the blockchain itself is the state. The script itself is stateless. It just facilitates transactions. It's very simple. You can't do anything crazy like that pre-sale idea or any other crazy idea that's happening on Ethereum right now. But you can facilitate low-level transactions. Now we're going to talk about the Ethereum virtual machine. This is essentially what facilitates these incredibly complex programs and contracts that have their own state, and these are actually executed on the peer-to-peer network that is the blockchain. This sort of architecture right here. There's an extremely detailed explanation of exactly how it works. I am not a network expert, like in exactly physically how it works or how you set up a virtual machine on each of these mining nodes to run the scripts that's being sent in from these addresses. Every time you publish a contract, essentially it's a transaction. So it sort of goes into the same field as this transactional data, except it's actually executed. And it can be called, meaning if someone wants to call a function of your contract, you know, they want to do this pre-sale, or they want to do a regular sale, or they want to read the state of the contract and all the things it's associated with. They essentially broadcast a request to either read or call those functions. Now, Ethereum is meant to specifically facilitate this. They have a theoretically infinite block size. So your programs can be as big as you want. You're just going to be paying a lot of money. Since this contract is sent as a transaction, the price you pay is proportional to the number of transactions. And it could be seen as just a bunch of transactions, the smart contract. You know, something like, you know what I think I can find is smart contract I wrote, me and my friend. I think I could just Google it. We made this NFT series called the Graveyard Sale. No worries, you can just go to the website. The website we made. I have the smart contract address somewhere on here. Probably should have linked it in the slides. As you can see here, that's not true. My MetaMask is messed up. If we go here, we can see actually how many are minted. So this is Etherscan. This is a list of all the transactions. Internal transactions would be transactions within the contract itself, such as the state changing, something like that. If you go to contract, you can see the code. So this is the raw code. This is how you're able to pretty much audit any smart contract. And basically, this code is mostly boilerplate. In order for, say, a site like, there's a site called OpenSea, and it displays the metadata associated with custom tokens. These tokens can't be fully custom, otherwise it would have no idea what it's looking at. So there's a couple tokens that it can use. The main one is ERC 721. It's just a specification for a boilerplate of functionality a custom token must have in order for it to display the data. And by custom token, I mean, it's the idea of tokens in Ethereum is you have little special packets of metadata, and they can be transactional. Like if the Ether is the transactional token, the base transactional token of Ethereum, you can make any token could be tradable like Ether. But each token might have a different form factor that represents the metadata it contains. This ERC 721 token contains things like, oh, I just copied it. I think there's cool. So if you go to, I think it's called set base URI. Let's see. Base. Basically, this takes in base URI, and this is a long contract, so I'm not going to search for it. We're already on code line 2200. But the URI is basically, when you hear about the idea of a non-fungible token, the idea is that it's a specialized token. It's something that can be stored on the blockchain, and it stores unique information. It's not just a general transactional token that's represented by a balance. You can have a number of them, but you can't have a type of them. In this case, you can have a type. And you could actually, in the metadata, include URIs, which are basically just links to other services. And so you could host it from your own website or from some other website or Google Images. And so, you know, you can put the URL to a Google image of a bear. But you know, you don't, that may not necessarily be at that exact URL forever. And also you probably don't own that legally. What this usually uses is a service called IPFS. I think it stands for Interplanetary File System. Sort of nerdy. A lot of the names you'll find, by the way, if you decide to develop smart contracts, are very strange and nerdy. For some reason, every single development environment tends to be named after food. There's truffle, brownie, ganache, and it goes on. But then it goes random, like hard hat and open zeppelin. There's like sometimes a strange line of consistency and then it breaks. It's weird. It's the Wild West. Basically, you're going to want to store image data on this service called IPFS. It's a peer-to-peer storage system. So similar in attitude as the blockchain, it stores CIDs, which are cryptographic caches of the data, or it stores the data in a URL that's represented by a CID, which is a unique cache. That's bounced around from peer to peer, so it's technically permanent. So if you include that IPFS link as your URI, that CID as your URI, not only can you set ownership of it, not only is it kind of hard to find, but when you link it to the smart contract, it'll be there forever. So not only is this unique data within a smart contract, but the data is there forever. And the exact structure, the way you do this, in case you decide to make an NFT smart contract, it's a little confusing. You set the image in an IPFS server, and then you set metadata, or the metadata is the URI. And then there's, it links to an image within the URI, and it's just in the structure of a JSON file. And that can be hosted anywhere. It can be hosted locally, so you can make changes to it, which isn't really that permanent, or you can host it on another IPFS link. Now, back to the Ethereum virtual machine. I'm doing on time. We're going over. All right, I'm going to speed up a little bit. It's a virtual machine that runs on a peer-to-peer network. How exactly that works, you can read that. It's complicated. It's hundreds of pages, I think. NFTs, we've already talked a little bit about that. Pretty much everything on this page. When you see ERC, it's probably an Ethereum standard token. If you're writing a smart contract for a specific token, you essentially just use the standard code as boilerplate. You can find the standard code on places like Open Zeppelin. Technically, it goes a little, so say you find an ERC 721 token on Open Zeppelin, it's essentially a open source repository of tested smart contracts. It'll include more than just the boilerplate. It'll include functions like, to mint and to read and to see a count of how many that may or may not be part of the standard, but you're going to want to use them anyway. So Open Zeppelin's a great resource to get this sort of base of your contracts. And now I just wanted to compare Bitcoin and Ethereum since we've sort of gone over both of them now. Ethereum, and it sounds like all pros on Ethereum's side, but this last part is sort of a big deal. Not only is it insecure, but you can argue that it's not insecure. Like the difference in security is Bitcoin is like pretty much physically impossible in 1 billion years, and Ethereum is like 1 million years, which neither really matter to us. But it can lead to centralization, which is sort of against the entire idea of crypto. I think they're continuously developing their environment to not allow that though. That being said, there's always new blockchains coming out. So just keep your eye on it, read the white papers if you really want to know. A lot of the news you'll try and find when you're researching these new blockchains is just based on the price of the base transactional token. Basically in Bitcoin, the base transactional token is Bitcoin because it doesn't support custom tokens. Ethereum, it's Ether. Solana, it's Sol. Cardano, it's ADA. I don't know what that means. I don't know why they chose that. That's all these, all this journalism will report on is what the next big thing is. But they have no idea why. I would just look at the security and functionality and potential of each blockchain. The reason Ethereum is blowing up isn't because, I don't know, it's more, it got a lot of buzz, it got a lot of social media. I mean, that definitely helped, but it's a very amazing new technology, even if I'm talking about how it's potentially violating the sort of philosophical ideas behind cryptocurrency in some ways. Yeah, you can just read through this. It's things I've gone over. They're both the same base idea. It's a long chain of crypto hashes using Merkle trees. You know, the transactional tokens act very similarly. Now, I'm not going to go into huge detail about this. This is originally what the presentation was going to be. But it's, I don't know, I could try a live demonstration. There's like a 60% chance it'll work. I decided instead to just include a bunch of resources. The hardest part about smart contract development is knowing what you need to do, what the development environment is. So I just want to go over that. And the rest is really just reading documentation, deciding what kind of environment you want. Two basic things you'll pretty much need that aren't really optional: Solidity and Web3. Solidity is actually the language you write smart contracts in. It's sort of a JavaScript-like and C-like. It sounds very strange. It's weird. It's the last 4 years, it's been changed so much. It's sort of hard to keep up to date with it. You don't really need to. Every update changes the syntax, but it compiles to the same code, although there are some deprecated features. So you don't want to code in old versions of Solidity, but usually all the resources you'll find aren't in the most recent versions of Solidity. So that can be a little difficult to tackle. Thankfully, OpenZeppelin has all these tested smart contracts, and there's a bunch of other open source repos that provide these smart contracts, these boilerplates for you. The code that you write in Solidity is compiled and deployed to the Ethereum blockchain. The way you do that changes a little bit based on what development environment you choose. I'll go over those development environments next slide. Basically, what you're doing is you're creating a program that floats in the cloud, that in this peer-to-peer network, and then you call functions. These functions can be private within the contract, they can be public to everyone, or they can be publicly callable, but they can only be, they're only valid when called from the owner wallet or some special wallet. So undergoing constant changes, so keep that in mind. Web3 is how you'll actually interact with these smart contracts. Technically, there's more API. But Web3, if you find a web application and it says like connect to MetaMask, or like Etherscan was displaying all those the read functions, that's done through Web3. It's a JavaScript API, library and API that allows you to interact, call smart contract functions, and do a bunch of connect to MetaMask and everything. MetaMask is a browser extension, that's a wallet. I'll briefly demonstrate that. There's a Python version. I think it's way easier, but it's not technically an API. It's essentially a library that looks like the JavaScript Web3 that connects to the Infura API, which is a separate API that you can use to interact with the Ethereum blockchain. It's very useful for testing locally. Can't really be deployed to servers, not easily. So JavaScript Web3 is sort of your go-to. I'll also go over, you don't technically need Web3 if all you want to do is call smart contract functions manually. You can do that through Etherscan. I'll see if I can demonstrate that. Yeah, and the cool thing is it can run on static websites. So it's sort of like a databasing system that's public, that you don't need to worry about security and like dynamic websites. You can just have a static website called smart contract functions with Web3, which is sort of the cool aspects of it.
Almost out of time.
All right, sorry about that. I'm just gonna explain what these slides are then. I'm not gonna demonstrate. I'll give you guys my email if you have any questions, if you decide to do this, because it can be confusing to start. These are the development environments. Remix is a sort of a full stack thing, does everything. Hard Hat is just for execution. Truffle includes test libraries, test scripts. Hard Hat also includes test scripts. It includes Ganache, which is these test wallets, so you can test locally. You don't have to upload to a testnet. Brownie is similar to Truffle, but it uses Python Web3. OpenZeppelin is this library. Web3 is this JavaScript. Etherscan you want to use all the time. MetaMask is a browser extension that allows you to interact with Web3. It's basically a wallet on the browser. That's pretty popular, pretty easy to find out about MetaMask. These are the two ways I recommend approaching this. Mainly, this is the way to start. Go to Remix, Ethereum IDE. You can pretty much there's test contracts. You can pretty much deploy and just like go to the website and then click deploy and it'll deploy as long as you have a MetaMask and you connect to a test net. It's sort of weird the way you acquire that, but it's pretty easy to look that up. You're going to want to go to Rinkeby test network, connect to that on your MetaMask, get test funds. You can just publish the boilerplate test contract, connect to your MetaMask, and then you can deploy it. You can interact with it if you just enter that address on the testnet Etherscan or directly from the Remix IDE. It's very good for testing, not really good for actually developing, because you can't really rapidly test when you constantly need to upload to this test network. You're probably going to want to use a local environment like Truffle or Brownie or Hardhat. You can use the test contracts from OpenZeppelin. You can use Ganache, which allows you to test pretty much instantly on your local network. It just emulates wallets. I spelled Hardhat wrong there. And yeah, I think that's it. Yeah, and here's just more resources. There's a great video explaining Bitcoin, and here's all the white papers. They're all great white papers. Our Cardano doesn't have a white paper, but they had their website explains it. And yeah, I think that's it. So I couldn't demonstrate, but if you just go to these resources, look up some videos, and I can write my email down right here. And I think that's it.
All right.
Oh, can I go behind you? Yes, that's .com. I recommend you guys try and get into smart contract development. Like, it's less risk than just dumping your savings into cryptocurrency, and you actually get to understand it. So yeah, go for it.
Zero or an O?
Zero. Yeah. Hostetter0@gmail.com. Yeah. Okay. Feel free to email you.
Right.
I answer what I can.
We'll take a few minutes break just so our next speaker can get situated.